Amit Kapoor. I basically these days teach data visualization, data science, all the fancy words next to it. So machine learning, deep learning. My background is primarily in management consulting. So I worked in India and UK in strategy and operations kind of consulting roles. So working for different types of industries, cement, steel, oil and gas, and then in UK I primarily worked a lot on consumer and retail, so what we call as CPG, consumer packaged goods, and retails, grocery, electronics, DIY. So I did that for about 10 years, and then that was all in the last decade. And this decade, I've probably been involved in teaching data visualization, storytelling in kind of open contexts like these, so open workshops. I also teach in corporate contexts. I also do teach in academic context, so kind of data for management students, and also for design students, which is more on the information visualization part of it, or interactive visualization. So that's a bit about me. The session was intended to basically try to think about linear algebra in a very visual way, and we'll see how much we can talk about it. And then we kind of go through that, but before we do that, just kind of go around the room, quick introduction, name, background, and what's your interest in learning this, because we probably all learned a bit of this in school in some way or fashion. And I know these days everybody kind of wants to know the math again, just because math seems to be important. So just, what's your interest and why are you doing this? That's it. Okay. Computational physics. Okay, so then you know all this stuff. No, there's nothing else in computational physics than manipulating vectors, tensors, I guess, more like it.
Yeah, linear algebra is a lot of physics. So I have an MSc in physics. So
okay.
My name is Anirudh, and I do study at B school.
Okay.
I haven't had any work experience, so to say before, at all. And yes, it sounds really interesting. Whatever we're going to discuss, it sounded really interesting. So I could learn something about it.
Mm-hmm.
Yeah.
Okay.
So my name is Sue. So I'm also B schooler.
Okay. We basically have people coming from that house to this house. Yeah. Yeah, true.
So I was working as a game developer with my job and trying to figure out what to do next. So running Clojure, and basically I also learned Scala and a bit of Apache Spark. I didn't do any machine learning thing, but did do some data analysis. So I want to see want to learn how. It's really interesting to know the intricate details.
Okay. The back?
Hi, I'm Jeet. So I used to work in a small startup called Geekush. Basically, we worked in CRM ERP solutions, and essentially we did have a lot of data visualization related products.
Right.
When I quit about a month ago.
Okay.
Right now I'm not doing anything per se. I'm just exploring things, and this does lie in my area of interest.
Okay.
Hi, I'm Vedant. So I'm a developer with HasGeek.
Hmm.
And I do a bit of ML on the side. So made one or two things for HasGeek and on the side projects.
Nice.
But nothing major, nothing too deep into it. And so I was looking more on the visualization side. I think linear algebra is which tools will you be using or what will you be using here? So
Say that again. So what tools will we be using to visualize linear algebra?
Like, yeah, what is visualizing? Like, okay, you know why you put it in the C, but what are we using it?
How do we visualize it? Okay. We'll try and see how much can we do on that. Yeah.
My name is Tamil. So I work in a software industry, pretty much on large scale data analytics.
Okay.
Hadoop, NoSQL,
Now.
Python, Spark. Now I started working on machine learning like classification algorithm.
Ah.
I feel like math is essential. So it is good like if we have multi-dimensional, like if you want to classify algorithm, like if you have multiple variables, so how can we visualize them?
Okay.
So as he said, like y equal to fx plus c, there is single x, let's find it.
Simple.
X1 to extend, like how to understand that visually.
Okay. So people pick this up as visualizing multidimensional data, is it? So you picked it up as this, you picked it up as this. Okay. What did you pick it up as? Visualizing multidimensional data? Oh, okay. Not linear algebra. Okay. There we go. That's a good start, huh?
My name is Bhavesh Gogoi. I'm a developer in Piping Nano. It's a startup company who provide smart piping solutions.
Sorry, say that again, huh?
Okay, my name is Bhavesh Gogoi and I'm Android developer in Piping Nano. It's a small startup company who provides smart piping solutions and
Smart packing solutions.
piping solutions.
Okay.
So I'm not from this domain, but I'm not good in maths also. But I like to take challenge and want to learn some new things. So and in future I want to go in machine learning. Recently I work in Raspberry Pi and Arduino.
Right.
So that's why I came here.
Okay. There in the back, lady.
Hi, I am Garima,
Hmm?
and I'm a front-end developer, not from this field.
Okay.
I am here partly for the speech, partly to help HasGeek.
Ah, right. Okay. Okay, so what should we do then now? Should we do visualizing multidimensional data or should we do visualizing linear algebra? We can do either. What would people like to do? Because, huh? Let's go with that. What is linear algebra? Okay, let's try. I'm going to use this board. So actually, if you think about machine learning or these days data science, a lot of the underpinning of how stuff is done is centered on, I guess, three basic parts, right? I mean, there is this idea of, obviously a lot of it is stats, right? I mean, machine learning is just relabeled stats by the computer science community in one way. It's the statistical people will call it statistical learning. So there's a lot of basic stats that, or all these algorithms that we use now are kind of statistical in nature. I mean, they've been all developed, some recently, or improvements have been done recently, but the basic algorithms have been done maybe even 15, 20 years back, right? So there's obviously a stats element to it. There's obviously a calculus element to it in the sense of the whole theory of calculus, right? In the terms of finding a gradient or finding when a curve reaches its minima, right? I mean, if you can think of that, like, you know, when does a curve reach a minima? You can think of it as when the slope of the line is 0, right? And so there's a lot of calculus that underpins it. And then there is a lot of linear algebra, which is kind of underpinning a lot of these operations that we do, like so linear transformation. Or at least that's where it starts from. And so let's take a very simple linear algebra and understand what it is. So what is a vector? Like, let's start with from there. Like, what is a vector? What is a vector? What is a vector from computer sciences? It's an array. It's an array, or if you're so if you say from a computer science hat, you will say, okay, a list of numbers. If I put the Python hat and I call it a list of numbers or a list of entities is, so any list in computer science is what they would call it as a vector. Physics. Who said who was a physics? Computational physics. Yes. What is vector in a physics sense? Right. So something which has a magnitude and a direction, right? This is how we think about in the physics domain, right? In terms of anything that has a magnitude and a direction, and we can think of a vector as, so is speed a vector? Velocity is a vector, right? So velocity, speed is only distance is direction, but velocity is a vector, right? So this is kind of like the physics view of it. This is the computer science view of it. Any list of numbers. And when it comes to data science, you'll often hear this word, we are doing vector operation. We're doing vectorized operation. Wow. And what's the math view of it? What is the math view of it? Come, sit. Anywhere. What is the math view of it? How do mathematicians, how do we, if we were to think of it in math, want to define a vector, how do we define a vector? Huh? No. So if I say a vector 3 and 2, how does mathematician define it? How would you define it? That's a computer science. Huh? 2 dimensions, yeah. There's 3 I cap or 2 AI. So if I have this as I, this is J. So I'm going to take this and this, and I'm going to make a point 3, 2, and go down from that side, right? So implicitly in a vector, what we assume when we talk about from a math perspective, and this is where we will largely be in, or at least initially to think about this, or geometrically, is we assume some coordinate system, right? We assume some coordinate system, 0, 0, and we assume that there is 3, 2 is where it ends up being. Right? Does that make sense? Right? So vectors have a few properties. So let's say this is vector, we will write it as this. So I just said a basic, and then we'll try and solve one simple equation and try and build an intuitive sense of what it means. What does it mean to scale a vector? So what is 2 times vector? Multiply every element by 2, right? So what does it mean to scale this vector is to literally, I mean, if you were to draw it, you'll kind of double it. But you can also think of it as scaling it. So my I vector is going up, my J vector is going up to twice of it, right? I don't know, this is 2 and 4 it should be, if I drew it correctly. And this should be 6, right? So 4, 6. Does that make sense? Okay, what does it mean to add a vector? So I add 2 vectors. What does it mean? So let's make a V vector. Let's call it 1, 2. You need another pen? 1, 2. So I have 2 vectors here. This is my V vector, W vector, and this is my V vector. What does it mean to add 2 vectors? Geometrically. So the idea is to learn here visually. So we'll try and learn as much as possible visually. So you build an intuition of it. What's the math? Okay, people will know the math. What does it mean to add two vectors? So here we said the vector answer is what? 6, 4, right? Lost it. Oh, that's right. Okay, what does it mean to add two vectors? What? Add all I components and j components. So we're going to do 3 plus 1, 2 plus 2. Okay? Yeah, is that? What does it mean here? So if we were to draw this 3 plus 1, that's 4 and 4. So it comes here. So our new vector, I need a third pen. Funny enough, that's also black. Okay, so we've got our third vector here like this, right? But geometrically what we have done? Okay, so we've taken the endpoint. So we've taken this vector, which is here, and we've taken this vector and we put it here. Yeah? Does that make sense? Does that make sense? Okay. So far with me? What does it mean to add two vectors? So, I mean, we can also scale them, right? We can also say, in this case, A times V plus B times V. If I, is this clear so far? These are the two fundamental properties of vector. And actually when mathematicians abstract it, they abstract it to everything when they call vector space. Anything that follows this and a few other laws is supposed to be a vector space, which could be anything. So the mathematician's way of thinking about it is to abstract it. What does it mean when I have this equation? So A times V plus B times W. What is this equation would mean? So here I just added two vectors. If I multiply it by A and B, A and B can be any value. What would they mean? What would it mean? Just a few basics. Okay, mathematically it's another vector. But for any combination of A or B, what does it mean? So if I choose some A, some B, right? If I choose A as 1, B as 1, I get this vector, right? If I choose A as 2, I can get another vector. Something here, right? I can get another here, another here, another here. Right? So I can get an entire vector space, right? Does that make sense? So if I take these two-dimensional vectors and I can choose any combination of them and I can span an entire space, so that's called the span of the vector. Is that clear? So just a few basic concepts, then we'll try and solve one problem. So what's the span of this vector space? These two vectors? How many dimensions? 2 dimensions, right? So can the span be less than 2? When can it be 2? When the j component? I or j are just a unit vector here. So this is I. This is I, right? This is I. This is j. Okay, we'll come and explain what I and j is also. When can be the span equal to 1? visually? What does it mean span is 1? Span is 2 means it's a plane. What does it mean span is 1? It's a line. How can these two vectors, when a sum of any two vectors be on a line when? So yeah, so when P, the V vector that we had here, and if the W vector also lies on this, or it could be in any direction, smaller or bigger, then you can see, so that's why when you say, okay, I have 3 comma 2 as 1, and if I had minus 3 and minus 2, this vector is just minus 1 times this vector. So they all lie on this line, so we call the span as 1. Does that make sense? Right? So in a vector space we have, so let's just, so we have span 2 and 1, few concepts. We have, this is called, they have addition property, they have multiplication property, and this coordinate system that we've chosen, I or j, is called the basis of the vector. Okay? Is that clear? Yeah? Just basic concept. So when somebody says, what's the span of my two vectors? Span of the two vectors means how much space can it encompass. When you say, what's the basis of my vector? It basically means, what's my unit vector I and j? In this case, you can think of it as 1 comma 0. So this is on 1 comma 0 and this is 0 comma 1. Right? These are my basis vector that we have. Right? Okay, and then the addition we understood. Span, basis, summation. Okay. Is that part clear so far? Okay, so now let's solve a very simple equation and we'll understand how this thing starts to become more powerful once you think in vector spaces rather than normal spaces. Anybody does 3D modeling here? 3D gaming? 2D gaming? No? Huh? And do you do a lot of matrix multiplication there? Rotations? No. Nothing. Okay. Okay, let's think of the most simplest equation and then we kind of try and understand. Let's say 2a plus 3b is equal to 12. Let's say 1a plus 2b is equal to 8. Is that okay? Does this, can we solve this? Can we solve this? Okay, how do you now traditionally, so we'll try and think about it in 3 different ways. Or 2, let's start with 2. How do you traditionally think of this equation? If you want to solve these 2 equations, which is called 2 linear equations for A and B, how do you think about it to solve it in a row way? Let's say we want to think about it in a row way, and then we come to the column way, which is the vector way of thinking about it.
Multiply the second equation by 2, subtract. The x will get cancelled and you get the value of b.
Multiply it by 2 and subtract, okay. Okay, so that's the Gauss elimination way. Okay, let's write that. So first one, E1, I'm going to write it as 2a plus 3b is equal to 12, and you're going to do 2 times equation 2, right? So you're doing 2a plus 4b is equal to 16. Okay, and then you subtract it. So you get basically 2a the first equation remains the same, and the second equation becomes 8 minus 5b. Is that what we? Oh, this is subtracted already. Yeah, okay. So minus b is equal to minus 4. Okay. B equal to 4. Then what do we do? Okay, so technically, I mean, if you're doing the math way, we do the forward elimination. So we do forward elimination in the sense we go down, and then we do backward elimination. So we subtract this. So this time we're going to do E1 and minus 3 E2. If you were to think of this is minus 3. So we get 2a is equal to 0. Did I get this correct? Yeah? Okay, so this is called forward elimination, this is called backward elimination. Nothing new in this. Mr. Gauss and Mr. Jordan invented this in 1600s. It's called the Gauss-Jordan elimination, way to do it. Okay, so this is kind of the math way of thinking it. We know all of this. How do we think of it geometrically? Okay, so let's do one way. So this is now, let's say this is kind of our traditional way of thinking about it. Okay, let's think of it in rows. Okay, how do I think of it in rows? Visually? So I draw the first line. How do I draw the first line? Yeah, put A is here, B is there. When A is 0, I get B as 4. That's 1 point. When B is 0, I get 6. Right, so that's my first line. Yeah, is that clear so far? What's the second line? So when B is 0, A is 4. A is 8. Okay. 6. 1, 2, 3, 4, 5, 6, 7, 8. Sorry, is 6. Okay, and then when A is 0, B is. Okay. Does that make sense? So we get this intersection point which is 0, 4, right? How do we think about it in column ways? What does it mean in a column ways? This is a traditional way. These are the row way. So I'm thinking like this. What's a column way? Can I write this? As this? Yeah? Is that the same? So A multiplied by this time, B multiplied by this time is equal to 12. So 2A plus 3B becomes 12. 1A plus 2B becomes 8. Right? Does that make sense? So this way is to try and think about them as lines. So if we had 3 A, B, C, we would have think of them as planes. Right? So we would here go from a line to a plane. Here, what are we thinking now? The column way? As a, what is now, this looks familiar to what we done earlier. What had we done? What does 2, 2, 1 look like? It's a vector way, right? So now the column ways, think of them as a vector. Now, so let's draw on some basis I and j, and now what do we have? 2 comma. Well, what's my first vector? So what am I thinking here? I want a linear combination. So if I was to write this as v and w, right? Does that make sense? Is this starting to look like a linear combination of two vectors? All I want is a linear combination of this and this vector, which comes to some vector u. Is that clear? So what's my first vector? Again, I start from 0, and this is 2 comma 1. So that's here. That's my first vector. What's my second vector? 3 comma 2. 3 comma 2. I'm going to make it 3 comma 2. Should have chosen better examples. And what do I want is the final vector, which is? So I'm going to make it very big and say 12 comma I. Right? So when you think about it from a vector way, what do you think? I want a combination of this. When I add this, multiply by something, scale it, and then add this, I should come to that vector. So far with me? Yeah? Okay, now what does it mean to so I'm going to erase the row view for now. So what does it mean to have a linear combination of two vectors? We can write this, and if we write this again as 2 comma 1, 3 comma 2, or 3. Is that okay to write like that? People remember this way to write? So what we're saying is, this is effectively writing it as this. I break, 2, 3 like this, equal to 12, 1, 2 equal to this. So far with me? Yeah? Okay, what does this mean to take a vector and multiply it by two new vectors here, 2, 1 and 3, 2? What are we doing here? We're basically saying I have a vector a comma b, which when multiplied by this converts it into 12 comma 8. Yeah? Is that with me? What does it mean to multiply a vector by this matrix? Well, okay, what does it mean in a linear transform? What does it mean in a linear transformation? What is a linear transformation? What am I doing in a linear transformation? I have a space which is linear right now, where my I vector is here and my j vector is here, right? That's my artificial space that I've chosen. I've chosen this as I vector here, j vector here, right? Put them 90 degree. What happens when I multiply this? Multiplying by A by B is to make this A times and B times and then multiply it, right? What does it mean to linearly transform it? Geometrically. Scale it and rotate it. Scale it and rotate it in any way, or scale it and rotate it in a particular way? What's the particular way? What's the constraint? What's a linear transformation constraint? In the same direction? No, not in the same direction. So when I take this coordinate system, right, and I linearly transform it, which means I move the I vector to 2 comma 1, So that's my new vector. So let's say 2, 1, that's 2, 1. So my vector has gone here, I dash. And my j vector has gone 3, 2, like this, right? What it has done is taken this coordinate system and squished it in a new coordinate system where I is like this and my j axis is like this. I should probably draw it with a different line. I'll draw the back line with a different line. So I had a 90-degree coordinate system like this. What it's done is it has transformed this I vector into this new vector and this j vector into this new vector. So this is a linear transformation in which if these spaces were equidistant, they are again equidistant in this new space. Different distance, but it means it's linearly transformed. If it transformed into some other shape, it would not be a linear transformation. But it is basically translating this A and B into, how many people are lost? Okay. Can I think of A and B for the moment as A times I and B times j here? Right? Can I think of this as transforming this linear space where my basis vector was I and j into another shape? So think of this as I had a coordinate system like this and equally distant like this. Now I have a coordinate system where the center is still at 0, but think of the original I has gone like this and my y have gone in another space, right? So you can think of this as rotating and transforming, it's scaling and rotating, right? So I could have scaled it and then I have rotated it. Does that make sense? So does that make sense? What is the magnitude of? So no, in scaling, okay, in this case, I mean, forget A and B here. If you just think of A, I and j, the scaling is by 2, 1, 3, 2. So it's basically moved that vector to 2, 1 and the 3, 2. So think of this as my original I, j is this world, and in that world, projected world, that I would point to this place and the j will point to this place. So I have taken a coordinate system, rotated it, squished it or stretched it in some way, right? Does that make sense? Okay, maybe it's easy to understand. What if I just reverse it? And maybe it'll be easier to understand that. If my original vector is this is j, this is I, in the new space I points to here, j is there, still there. How does this look like? I'm doing this really fast. How does this look like? What would be my vector matrix here? Minus 1? What? Minus 1? Huh? Minus 1 comma, right? What does this matrix do? So I had anything in this vector in this space, it is transformed it into the reverse space. Does that make sense? Yeah? Does that make sense? So when we think of linear transformation, you can think of this matrix as just trying to project my basis vector into a different coordinate system. That's what linear transformation is. And the reason it's linear is it is scaled equally and it's spread equally in that direction. So it will be stretch or squash equally So the distance of equal points, so if you had a number line with 1, 2, 3, 4, 5, in the new coordinate system also they are equally spaced, differently equally spaced but still equally spaced. That's the only condition. That makes a little sense, right? So far with me? Yes, no? Okay. Is that this clear that what we're doing when we're multiplying this equation is just transforming this into a new coordinate system. So we're taking an original vector space which is I and j and now moving it to another one which is defined by this projection. Okay, does that make sense? Okay, so let me then, how many are already, this is too much, too lost? Okay. Let me try and rewrite this part and we will understand a bit. So what was my original equation? 2, 1, 3, 2, AB is equal to 12, comma 8. Okay. Yeah? What did I do here when I multiplied this equation? E1 minus 2 times E2. What does this give me? Does it give me correct? 2, 3 equal to 12. 1 minus 2, right? Is that okay? Can I write this equation like that? So what am I doing? I'm taking this vector and projecting it into another space and I get my new vector, new space. So far with me? This equation is nothing but this, right? We understood. So what I'm doing is I was projecting this to this. Now I'm projecting this to this. Is that okay? What is the final operation I did here? The second elimination that we did? We have to do it on that side also, right? We're projecting on both sides. We do it this side, we do this side. Okay, what is this operation? What matrix would come here? What should I write? What should I write here? One. One. Is that correct? Yeah? Correct? Yeah? So far with me? Is that okay? So I take this vector, I project it with this, then I project it with this. Okay? And I should technically, if I do all the math, I should just get A and B there equal to 4, 0, comma 4, right? With me so far? Okay, instead of multiplying this first and then this first, can I multiply this first? Yeah? Okay. What if I multiply this? What do I get? 1 minus 2. 1 minus 2 minus 2, 6. Yeah, I'll get the same thing that side. What is this? Multiply by this. So we typically think of this as capital A x equal to B. After 1 it should be this one, no? Did I make a mistake somewhere? Huh? Is this correct? 1, no, it's come to 2, 3, minus, I think we wrote that vector wrong. I multiply this one, this is 1, that's 0.
Now these two matrices multiply 1 into 2 plus 0 into 1 is 2, right? First will be 2.
Which one?
This right matrix here will be 2 and then 3.
Say that again. Oh, it should be half into this. Ah. This is better. Minus E2. Say that 2 minus. Yeah, minus half. So this should be half. So we have to write this as half. Sorry. It should be half. Sorry. Okay, is this correct now? Half and half. Yeah, this is fine, right? So let's multiply this, we get half, and here we get 0, here we get minus 5 by 2. minus 5 by 2, and here we get minus 6. Is that the inverse? Only 6. So that's 1. So you multiply this, we get 1. And we should get 3 by 2. Oh, we did something wrong. It should come to one identity matrix. 1, 0, 0, 1. The other side. This one? Should be minus 3, right? Half minus 3. Yeah? Okay, we made some mistake somewhere. Who can pick it up? So much for doing it on the board. Huh. 1 comma? This come.
Second line, 1 comma 1, 0 comma above.
This one, I was trying to 1 times E1 minus 2 times this. So we do 1, 2, 3, 2. So if we multiply this, we should get 2, 3 into 2, 3. Yeah, 3, 1A, 2B plus 3B, that's fine. And the second one is 1 comma 2, so that's 0 plus minus 2 we get minus 4. Yeah, we get minus 4. That seems okay. Minus 4 is equal to minus 4 here, right? That's what it will come. So I guess a better way to write this would be half.
That is the one below is minus 4b equal to minus 4.
Yeah, 4b equal to 4.
Minus 4b, right?
Minus 4b equal to 4. I think better, I mean we can write it as half, then it will be probably better. This should be minus half and then wait, this is correct, right? We got this should be minus, sorry. Oh. I'm 2, 3, that's fine. No, that's fine. This is fine. So you get 4. But it's better to do it as 1/4. So if we do this as half and this is 1. If we do this as half, we get 3 comma 2. We get this as 0. And we do this, we get 3 by 2 minus 1. That's not correct. I think we have a scaling issue. I mean, if we divide it by 4, it will be better. Okay. Sorry. Basically, we're not getting this matrix right. Technically, it should come to 1 by 4. 1 by 4. Bhargav, little help. What is wrong? Huh? You're lost?
I think after the first
1 minus 2
and
and 2 3
1 2. Oh, that's 2 3 1 2. No, that's correct.
yeah, so once you like multiply that whole thing, like if you just write it out maybe.
Yeah, we'll get this equation 2a plus 3b equal to 12, 4b equal to minus 4.
And on the other side it is 12 and minus 4. So now we have to on the other side what do we need, like we can choose according to that. Like what should we multiply now? I think this step is.
So instead of minus 4, we can get, if we get half here, let's say. That's better, right?
That matrix is representing an E1 and minus E2, right?
Minus 2e2, yes.
Yeah. So then the first one was correct, I think.
Yeah, no, but because we get minus 4b by minus 4a, right? I want to remove the 4 also. Then we get b equal to 1. Does that make sense? Because at the end, I just want a and b to be here. Then we get the inverse matrix on this side. Right now, we'll be left with 1, 0, minus 4 something, which is fine, but it doesn't solve the a into a inverse thing that I wanted to show. Anyway. Yeah, say that again.
Why don't we actually take the inverse and multiply it with the others?
हाँ, so वो तो कर ही सकते हैं, वो तो फिर then the computer will do it. No, I was trying to link the Gauss Jordan to the inverse, right? Okay, let's say, refer to the repository I have on GitHub for more details. But the idea here is, okay, so let's build on this intuitively, because we know what we did here with these method, or what we're trying to do here is just, let me erase this for a minute. Once you multiply this, we are basically saying, if I was to write this as ax equal to b, this is what we solve as the classical equation. I'm saying ax equal to b. I have an inverse, which if I multiply on both sides, right, it basically converts this x is equal to a inverse b, right? This is how the computer solves it. Actually, the computer doesn't use Gauss Jordan. They will use UDF and different ways to optimize it. So calculating the inverse is the hardest part and is the most compute intensive part of linear algebra. So how to calculate the inverse? There are many other ways to do it, which usually you'll learn. Okay, but does this make sense? So what we are doing is, I'm trying to look at, in this case, translate A inverse A into X equal to, so X is equal to A inverse B. So inverse is just a projection matrix which when multiplied with another matrix gives me an identity matrix, right? Does that make sense? When is that case? When is that possible? When is this possible? When is an inverse possible?
When A is invertible.
And what does it mean A is invertible?
Determinant is non-zero.
What does a determinant of a matrix mean? I have a matrix 1, 0, 0, 1. What does it mean? The determinant of this is what? People will know what the determinant. Multiply this by this, this by this. I get 1 minus 0, that's 1. What does it mean, the determinant? Okay, one way to think about this is I have a vector I and I have a vector j on this. So my first is 1 comma 0, which is basically this much. The second is 0 comma 1, which is this much. The area geometrically of this is the determinant. The area made by this two vectors 1 comma 0, 0 comma 1 is my determinant. Does that make sense? So what does it mean when the determinant is 0? Area is 0. How can the area be 0?
Span is less than n.
Span is less than?
If span is less than n.
So in this case, span is not 2 but 1. When is a span 1? When they both fall on the same line. So if they end up falling on the same line, then obviously the area between the two vectors is 1, 0, right? So when we say a determinant does not exist, that means we're basically saying this area is equal to 0, right? That makes sense? Okay, what does it mean if the determinant is negative? Can we get determinant equal to negative? 1 minus 2, 0 minus 1. Why? It's minus 1, no? Is it plus 1? Why? I multiply this one into this, that's minus 1, and plus 0, that's minus 1. Okay, so now what is that vector? When I multiply my I and j by this, what's happening? My initial parallelogram is 1, right? My I is unit vector. When I move it to 1 minus 2, what happens? My I moves where? Where is my I moved? 1 minus 2, right? So my I vector now is here. Where is my j vector? Zero. So my j vector is here, right? So now I'm saying it's the area between this, right? The area may still be 1, but why is the sign negative now? How do we interpret the sign? But
the first quadrant will be positives and the second and third quadrant will be
okay, that is one way to think about it. Nah, I mean that's still very, but geometrically what does it mean? Because we're just trying to build intuition geometrically, right? What we did is we took our basis vector I and j and projected it. In this new projection coordinate system, we find that the basis vector area is minus 1. So the area is 1 makes sense, but what does the minus 1 mean? How did we project the vector? So in this case, j is before I. In this case, j is after I. What does that mean? Just plain, like geometrically, clockwise, okay, clockwise, yeah. So we've turned the direction, but what does it mean when I rotated it? So I projected my I and j into this, but what did I do to make it different? How did it change direction? How can I change the direction? So I have I here, j here. What should I do to this plane to change it? But if I do like this and this, it doesn't matter, right? It is still, the ji is after it. What do I have to do for it to? You have to reverse it. So you can think of when the negative it means is when you, j is after I, but think of it as a plane that has now got flipped. Does that make sense? Yeah? So what I'm doing is I'm projecting my I vector and j vector, but now my plane is basically flipped. So what is determinant? What is determinant of a matrix? Now that what is determinant? Is the area formed by the basis vector in my new space. So the area is the determinant, and the sign is just whether I is in this, whether the transformation makes it remain the same or whether the transformation flips it, right? Now we are doing two dimensions. How would you think about it in 3 dimensions? I know many of you may think of the left hand rule and right hand rule. I don't know how many remember. The I vector here, j vector here, k vector points on the top, and if when I flip it, I and j and k turn around and I go from a right hand rule to a left hand rule, that means I have flipped it. So that's the same thing from a 2 dimension to a 3 dimension, right? Does that make sense? Right? So the idea of thinking in terms of vectors and trying to thinking in terms of geometry is much more to build intuition around how these transformations are happening. Because bulk of what we do in at least initial machine learning or any data science is linear transformations. Like if you're using any linear models, all you're doing is a linear transformation of the space. So linear transformation is basically trying to project my new x and y on my new basis vector into a new space. That projection is just linear, right? And now obviously you will argue we're only doing 2 variables. So that's the challenge of visualization. Visualization works till about 2, maybe 3 at best. After 3, it's really hard to visualize intuitively how it is. There are ways to do it. Like the way to do that is then to break this parallel coordinate system, this Cartesian coordinate system and make it parallel. But it's still not very intuitive. But the idea to learn this visually is basically to build some intuition around what it means when we are multiplying 2 vectors. What does it mean when we are saying a determinant of a vector is 1 or 0? And once you build that intuition, then it helps you to translate it when you go back and do. Because the math you all have learned. If you've forgotten, you will learn it back again. That's not a problem. You will figure out how to do the matrix multiplication, how to do the inverse. But the idea is to understand what's happening when we are really changing. Because when you go up, you will also then come with, null space, column rank. I won't go into all of that, but there will be other concepts about matrices that will become important, especially when you do unsupervised learning and kind of think about transformations to do it. But anyway, is this helpful in a way to think about it? So you want to go back and think geometrically as much as possible. What happens when I'm multiplying a matrix to a vector? Right? What really is happening? How is this projection really happening? Now I probably have done not a great job at doing this in this short time, but I would recommend you go and see this video by 3 Blue 1 Brown. I'll write down the name. 3 Blue 1 Brown. This is what I recommend as 3 Blue 1 Brown. The video series is called Essence of Linear Algebra. This is also Essence of Calculus if you want to check on YouTube. He basically does animated math videos and it's really nicely done. I mean, there's also now a series on deep learning. There'll be another series on probability later on. But his is really animated and much more visual than what I have done so far. But really look through it. It's not so long. It's about maybe an hour and a half in terms of all series. But it's a fantastic reference and most people refer to it for people who want to learn the linear algebra before going into learning machine learning or deep learning, right? So ML or DL, right? So because what we just solved, for example, AX equal to B, or revised in some way because all of you would know, is when we solve this for, right now we had 2 variables and 2 equations, but if you have n variables and p equations or p plus 1, then it becomes linear regression and we go on and build from there, right? So what we solved as 2 cross 2 or n cross n problem, when it becomes n cross p plus 1, then it becomes, I have 7 lines, and now I'm trying to find a solution for this, and then there will be no exact solution, but then you will approximate based on the least error and find one solution. And then we basically extend linear algebra, apply calculus a little bit of matrix calculation, and then we start to learn this. Right, so it kind of builds on from there. So if you at least have some basic understanding of all these concepts, basis, span, projections, and what we just, for example, one rotation share, they're like basic projections. Column rank, null rank, which we didn't cover, and then a little bit of dot product, and the idea of dot product, and the idea of cross product, and the idea of projection. I think this much is enough for you to have a basis, and then you can go and revise a bit of calculus, and then you can go into ML if you really want to. You don't need to know too much math, at least initially, but it helps to know all this, so then you can make judgments on all of that. If you want to know all of this in Python, we have a repository called Amit Caps is my GitHub name, so I'm pretty much Amit Caps. And there's a repository called HackerMath, which has this Jupyter notebook. I think I just did like half of one notebook there, and there are like probably 30 notebooks there. Not 30, how many? 20, 25 notebooks. So we just did one inverse calculation so far. The answer there is correct as opposed to what I did on the board here. Okay? Yeah? Questions? So these are the courses. There's also a few more interactive books on linear algebra, which I'm forgetting now, but I had shared earlier. I think this should be enough to get started. Our repo on HackerMath, on 3 blue, 1 brown. We're also doing a more detailed, this is just like a precursor, we're doing a more detailed 2-day workshop tomorrow and the day after. That's paid, unfortunately, or fortunately, but whichever way you want to look at it. It's a 2-day one in Kormangla. If you want to attend, you can just go to HackerMath link on the 5th elephant, or go to my website amitcaps.com, and from there you can go to HackerMath link. But you need to pull the trigger today if you want to, because we'll be doing it tomorrow at 10. Okay. Questions? Or we can wrap. Yeah, applications of this. So when what we just solved, as I said, this Ax equal to b for a 2 by 2, right? 2 equations, 2 variables. When we have n equations and let's say 2 variables. How do you solve this? This becomes linear regression, right? So that's one application of here. Like, so this goes to this, and then linear regression, we add a little bit of calculus, it becomes regularization and L1, L2, and we add a little bit more transformation, it becomes logistic regression. And what we just did as projections, for example, when you multiply one matrix by another, and how do you get that projection, and if we learn a little bit more of eigenvectors and eigenvalues, then that becomes PCA in machine learning, which is an unsupervised dimensionality reduction technique. So that's just the direct link from, so you go next step, that's linear regression. You go from one projection in a way, projection of the correlation matrix of, and I'm using these terms which I'm showed, correlation matrix of your features, and you apply that becomes PCA. So if you learn this, you learn eigenvector, then you would be very well placed. And, oh sorry, I didn't refer. If you really want to learn linear algebra, really, then you have to do the MIT course on OpenCourseWare by Gilbert Strang. On any of his books, there are 2 books, Linear Algebra for Optimization and Linear Algebra Basic, but there's an MIT open source courseware a course by Gilbert Strang. It's 23 lectures, 24, huh? 35 lectures.
But some of the things are recaps and exam reviews. It's an actual course they recorded it.
But you should see him teach. He's amazing, and he's got the two finest book on linear algebra is one, both by him. Like there is one on just linear algebra, and there's one on how you use optimized linear algebra for computation. Like how do you do it? Both those books. So I think once out there maybe.
Also a linear algebra course from fast AI.
Ah, that's more for computation, right? Maybe, but this is basic. This is basic and this is basic. Well, I mean, his level is MIT level basic, but it is still basic.
No, that version is like really, really simple.
What this row way, column way, and solving A cross N is probably the first 3 lectures there. Yeah. I've just done it. I was trying to do it fast, but the first 3 lectures is row, column, elimination, Gauss Jordan. Yeah, those are the first 3 lectures there. Okay. Really recommend if you want to be good in this math, just build a little bit of this basic, and then you'll find application. So if you do computer programming, and anybody wants to do plays with 3.js, or you do 2D gaming and you want to do rotation. So in 2D or 3D programming, computer programming, you basically have scaling, rotation, and transformation. So anybody who does anything with computer programming, and all you try to translate your scaling, rotation, and translation, which is shifting away from the coordinate system. That's all you do in 3D programming, and which is all done by matrices. So you need to know how the matrix translation is happening. So how to think of the projection happening in another space. So there's also that application if you want to think about. So anybody who does 3D modeling, 3D gaming I don't know, but 3D modeling for sure. Or if you're a JavaScript guy, you use 2.js or 3.js. That's all about this. Okay. Thank you so much. Hopefully it was